Okay, so we have a higher level question here. 3D graph below shows a molecule of methane. The 4 outer atoms shown in blue, are located on the vertices of a tetrahedron. Okay, so if we drew it in here, that's our tetrahedron. Every single one of them. So tetrahedron is equilateral triangles. Okay, so drawing on the right shows the projections of regular tetrahedron without the spheres. Okay, so we don't have the spheres on it. That's fine. So we need to draw an auxiliary plan on the given x1, y1 line. So we're given x1, y1 line to show the dihedral angle. So that's the angle, dihedral angle, between the two planes. So if we looked in here, we would see the angle between these two surfaces here. So the key point here, one some people have came across. So the key point is looking along, any line parallel with the xy line is a true length. Okay, so it's a true length in elevation. Okay, so it's true length in elevation. So we have a line here, AB is parallel to the xy line, so it's a true length. So this is a true length in elevation. Also, if we had a line parallel in elevation, it would be a true length in plan. Okay, so it's a true length in elevation or plan, dependent on where it's parallel. If it's parallel in plan, it's true length in elevation. If it's parallel in elevation, it's true length in plan. So we need to look along, so we're looking down along this true length line, okay, and projecting out an auxiliary plan. And once we see that as a point view, so we're looking down through AB as a point view, so it'll appear here as a point, we're going to get the dihedral angle, so the true angle in here. Okay, so same as any other auxiliaries, elevations or plans. We just have to make sure everything is perpendicular to the new x1, y1. Okay, so we know A and B are on that point. We know that C and D are going to be parallel, so project our points out again, parallel. Okay, so we're producing an auxiliary plan from elevation, so we have to take our distances from plan. So we need to get our distance from A and for B. So here's B. So B and A are the same distance and are also on the same line. So there's A and B. We need to get the distance then from D. Okay, so D is on that line there. So that's D, and we have the distance then from C. So C is also on that line, and that's C. Okay, so if we join all our points back together, C to AB, and then D to AB, our dihedral angle is going to be given to us here. Okay, so that's step one of it. So now we need to draw the projections of the largest possible sphere that can be contained inside. So it's inside the tetrahedron. So we're inscribing it. So if we look in here, if we're looking in here, we can see that we will have a sphere in here touching the surface, because we have covered this, if you can remember. Your tetrahedron, when it's drawn and you have a sphere inside, it's going to touch in the center, and it's going to touch the center of each surface. Okay, so the first thing we need to do is bisector angle here in this corner CD. So bisector angle. So the angle bisected it. Okay, we know then our center point, or the center of our sphere, is located below A. So we just have to bring A down. So we can bring it down into our plan as well, because we're going to need it. And that is going to give us the center point of our sphere. So the distance from here to the ground is going to be our radius. So we need to take that with our compass, spin the sphere. That's the largest sphere, then it's going to fit inside that tetrahedron. So there it is in elevation. We know the same radius, and the center point is on A, so we can spin it there in plan. Okay, and we don't need to put it into our auxiliary plan. So we have it in our elevation plan. So don't forget the key point. If you have a line, any line parallel to the XY line, it's going to be a true length in the other view. So for example here, A to B is parallel to the XY line. So A to B in elevation is going to be a true length. So from here to here is actually a true length. Okay, that's one key point. Then we have, when you inscribe a tetrahedron, a sphere inside a tetrahedron, it's going to touch every center surface, center of every surface. Okay, and the center is always located below the apex.